So the next feature that pushes this a little further is Superscalar Execution, and it's also called Superpipelining. Okay, what happens in this is that the processor, if it determines that there are instructions, like in the previous example we saw add R1 10 and add R2 5. So if it's able to figure out that these instructions have nothing to do with each other, right, then it can actually execute them both in parallel. So you have instruction fetch, decode, and execute, and simultaneously you could be doing you could do the instruction fetch, decode, and execute for the second instruction. Right, so you could do both of these in parallel. But what does this require now? This requires multiple logical units, right? So you need multiple hardware for each of the stages, right? Because you want to be fetching 2 instructions at a time, you want to be decoding 2 instructions at a time, you want to be executing 2 instructions at a time. And of course, if you have something like, let's say that the second instruction, instead of add R2 5, it was, let's say, add R1 3, right? Then could you execute that in parallel along with the first instruction? So you could do the instruction fetch in parallel, right? There's nothing wrong with fetching both these instructions in parallel. You could decode both these instructions in parallel, right? But while this first instruction is getting executed, can you execute the second instruction? No. Essentially what happens in this case is that for the second instruction you have to execute a no-op cycle. No-op is no operation, right? You have to wait because it has a dependency on some other instruction, right? And then you could execute in the next cycle, right? Once 10 has been added to R1, then you could add 3 to R1 in this cycle, okay? Can you think of some examples where this kind of architectural functionality would be very useful? So one common, a lot of common operations is when you're doing linear algebra operations, right? When you're working on matrices and vectors, right? So suppose you're trying to scale a vector or compute a dot product. You have lots of operations which are very similar in nature and which are completely working on independent data sets, right? So for instance, if you are computing the dot product of 2 vectors, A and B, right? So what do? You pick up the first element of each of them, you multiply them together, you pick up the second elements of each of the vectors, multiply them together, the third elements, and so on, right? So each of these is independent, right? Yes, you want to add them up finally to one common value, but there are easy ways you can design easy algorithms to take care of that, right? For instance, you could keep track of the result of, let's say, first half of the vector in a separate variable, and you could keep the dot product of the second half of the vectors in a separate variable, and in the end you could add them up together, right? So you can parallelize this to a large extent. So when you're doing the operations on the first half of the vector, and if you're doing the operations on the second half of the vectors, they are very much independent, right? They don't have anything to do with each other. So you could possibly rearrange your code so that the instructions for the first half and the second half get executed together. And that would make very good use of superscalar execution. So what are the issues that we typically face with pipelining and with superpipelining? So there are several issues. The first one of them we've already seen is data dependency. This can take various forms, but one of them is that, for instance, over here, right, we were adding 10 to R1 and then we were adding 3 to R1, but you could not add 3 to the register until that register was not free, right? It was already participating in some operation. Something was being written into that register, right? So you could not, perform that execute cycle at that point in time, right? So there are different kinds of data dependencies. So we will talk about them later. The second issue is branching. So what are we doing with these pipelines, right? So we are filling up these pipelines. Let's say that these are the cycles, and this is how the pipeline, how the instructions are getting executed, right? So let's say that we've issued 2 instructions together. So this is superpipelining, and then in the next cycle we issued 2 more instructions, and in the next cycle we issued 2 more instructions, and at some point of time what we realize is that this particular instruction, let's say, was a branch instruction. Right, when you decode that instruction, you realize it's a branch instruction. So what happens now? So what happens is that the instructions that are executing before it, they are fine, right? They have to be executed anyways. But what about all the instructions which are being executed after it? So here we are assuming that, you know, the processor is just picking up the instructions in sequential order and putting them into the pipeline. So what happens to all these instructions which come after the branch instruction? So you have to basically get rid of them, right? Because you are going to jump to some other piece of code. So these instructions have to be thrown away. So that's wasted work, right? You picked up all these instructions, you put them in the pipeline, but eventually, you know, that was wasted. You did not complete these instructions. You could not finish them. Another issue is memory latency. Well, this goes beyond pipelining. This is an issue in general. The problem is that the processor operates at frequencies of, you know, something like 3 gigahertz, 4 gigahertz, right? If you do some memory operation, right, if you want to fetch some data from the memory, it takes a substantial amount of time for that data to come. It can take hundreds of cycles. Even though your instruction can execute in about 4 or 5 cycles in 4 or 5 nanoseconds, but just because it is trying to get something from the memory, right, just to get that data, it can take hundreds of cycles. Right, so there's a huge gap between the performance of the processor and the time it takes to get data from the memory. Okay. So what will happen to pipelining in this case? Let's say that I have an instruction, say add R1, but instead of adding a value like 10 to it, a constant, which you know I don't need to go to the memory for. Suppose I'm trying to add to register R1 data that resides in memory location 1000. So what would happen over here? What would happen in the pipeline? Well, you would have the instruction fetch, you would have the decode, and then you would have the operand fetch. So what does operand fetch do? It fetches the data from the memory. How long is this going to take to execute? Well, this is going to eat up about maybe 100 cycles, right? So what happens to the next instruction, which was put into the pipeline after this? Instruction fetch, decode. Let's say the next instruction was add R1, 3. So what do I do now? I can't execute that instruction. That instruction is waiting also for R1, right? So it's also stuck. Only when this data comes and finally this instruction gets executed, after that can I execute this instruction. So when we talk about superscalar execution, right, what are we trying to do over here? We're trying to issue multiple instructions together. I'm trying to pick up 2 instructions and execute them together. Now, if I'm doing in-order execution, right, what is in-order execution? In-order execution is that I'm simply picking up the next instruction which is there in the code and trying to execute it. I pick up the current instruction, I issue it, I pick up the next instruction, and I have to check, can I issue it simultaneously or not, right? Maybe I can, maybe I cannot, depends on the dependencies, depends on various things, right? But I may be able to issue it, I may not be able to issue it, right? And you know, the chances of being able to issue the next instruction together with the current instruction may be quite small. So how do I deal with that? So typically what is done in modern day processors is that there's a window that is maintained, right? So if this is your code, it generally maintains a window of a few instructions, and it examines all those instructions and figures out that which are the instructions that can be picked up to be executed in parallel, right? So if this instruction is picked up, maybe the next instruction is dependent on it, I can't pick it up, but maybe the instruction after that is completely independent, right? So then it will pick up that instruction and issue it together with the current instruction, right? So there are lots of intricacies involved which we are not going to get into. For instance, you can issue instructions in different order, but you have to be very careful that they complete in the order in which the code appears, right? So we are not going to get a whole lot into those intricacies, and this is actually called out of order issue because it has issued instructions which are not in sequential order as they appear in the code. So another way of handling the same situation is VLIW, very long instruction words. So what happens here is that just as in the case of superpipelining, right, you were trying to issue multiple instructions together, but who was determining which instructions can be executed together? All of that was being done by the processor at runtime, right? When it was seeing the code, at that time it was maintaining a window and trying to decide which instructions can it execute together. So that makes the hardware complex, right? That makes the logic complex. So instead, another approach is that offload this to the compiler, right? Why don't I do it in the compiler? So when I'm compiling the code, at that time I can look at all the instructions and figure out which instructions can be executed together and just club them up together, right? And that's the idea behind VLIW architectures. So here you have instruction words which actually comprise of multiple instructions. Instruction 1, instruction 2, instruction 3 and so on, right? And the compiler figures out that these instructions have no dependency amongst them and therefore I can issue them together, right? So there are advantages and disadvantages of both these approaches. So if we just compare VLIW versus Superpipelining, right, being done dynamically, what are the advantages or disadvantages? So one is in Superpipelining, this involves a more complex circuitry. Whereas in VLIW, these decisions are not being made dynamically, it's being made by the compiler, right? So the circuit can be much simpler, the hardware can be much simpler. Again, when you're doing Superpipelining, when the processor is trying to determine which instructions to issue dynamically by itself, right, it's doing this in real time, right? This is in real time, whereas this is offline. And because it's doing it in real time, there's a limit to what it can do, right? Because it has to eventually, I mean, it's looking at the code and it has to issue the instructions in the next couple of cycles, right? So there's a very small window in which it has to make the decisions that which instructions am I going to pick up to issue simultaneously, right? Because it's all in real time. But that's not a restriction when you're doing it in the compiler, right? Because in the compiler, I mean, it's being done offline, you can take your own sweet time. Yeah, the compilation is going to be slow, but that's fine. But you can take your own sweet time and you can, look at a larger window, you can try to look at more permutations, combinations and figure out which instructions can be issued together. But of course, one major drawback of VLIW as opposed to Superpipelining is that it does not have a view of the dynamic state, right? That what is currently going on, because when you issue an instruction and let's say that the data is not present and you have to go to the memory to fetch that data, which takes a substantial amount of time, right? Based on that, you can make decisions of which instructions you can issue and which you cannot, right? So also the branch history plays a role. So again, we're not going to get into that, but previously whether a branch has been taken repeatedly or not, like for instance in a loop, when you're executing a loop, a tight loop, right? You take the branch again and again. So that that information is maintained in a branch history table, based on which you can, when you're executing the instruction, you can say that, okay, I've taken this branch condition, I've taken this loop 10 times before, so I'm probably going to take it again. So let me fetch the instructions from there and start working on them, right? So this kind of dynamic state is not available to the compiler, right? So whereas that is all this information, because it's being done in real time in Superpipelining, it is available to the processor, so it can use that information to make decisions.